Okay, so now that we have two different enantiomers of the same chiral, how do we differentiate between them? So here we have the two different chirals of Carvone, Caraway, and Spearmint, and the way that we can actually differentiate between two different types of Carvone, two different enantiomers of a chiral, is through classifying them as either R or S. And we do this using rules called the Cahn-Ingold Prelog rules. Now, how do we actually use these rules to define them? Okay, well, let's draw Caraway as an example. So we have CH3. Okay, so what defines a chiral again? It's having a central carbon molecule surrounded by 4 different groups, normally single bonds because we need 4 different groups. So here we have this carbon. This is the one that makes it a chiral. We can tell that because here it has one group going down, different group going to the left, another one to the right, and because it's 3 single bonds, we know that it must have 1 hydrogen in the back. Now this is actually quite convenient for us, because in order to use the Cahn-Ingold prelog rules, the first thing we have to do is order the different strands going off of it in terms of molar mass, and the way we do that is by atom from each branch. So let's take the first branch, this one, the hydrogen right here. So this would be hydrogen. This one on the left goes to another carbon, so we would have carbon for this one. The one on the right also goes to carbon, and the one down below also goes to carbon. So from this, we can instantly tell, because hydrogen has a lower molar mass, that this is 4th. And we rank these from 1 to 4, in terms of decreasing molar mass. So we can denote this with 4. Now we go on to these 3 because they each have a carbon. We go to the next molecule. So this on the left branch also goes to carbon. This one on the right branch also goes to carbon. And so does this bottom branch. They both go to carbon. Now let's take the third molecule. This one goes to a third carbon on the left. This one on the right instead goes off to an oxygen. So we denote that with an O. We see that this is therefore greater than this. And this final one goes carbon to carbon, and then to hydrogen. So here, this is our differentiating atom. This one goes oxygen, carbon, hydrogen. So we can rank that order of hydrogen, carbon, then oxygen based on their MRs. So now that we have that, we can then fully order all 4 of them. We order this once more using a 4. Then the one that has oxygen is first, and then the one with carbon is second, and the one with hydrogen is third. Now what the Cahn-Ingold prelog rules state is, after ordering them, you place the one with the lowest molar mass, in this case hydrogen, behind of you, and you look at the remaining 3 of them, and you look at the order from 1 to 2 to 3, whether it goes clockwise or anti-clockwise. And now it will always go either anti-clockwise or clockwise, because it's a carbon atom surrounded by 4 single bonded other groups, and that will always give a tetrahedral arrangement which will correspond to either clockwise or an anti-clockwise direction. So in this case, it's quite convenient because we already have hydrogen pointing to the back. So in this case, we only look at these 3, 1, 2, 3. So looking from 1, get another color, 1 to 2, 2 to 3, and 3 back to 1. So this is anti-clockwise. And if it's anti-clockwise, we denote it with an S. And if it's clockwise, we denote it with an R. So in this case, we then deduce that Caraway is in fact S Carvone. So let's apply the same thing to Spearmint, and we should get a different result. Okay, let's draw this out again. So we have Spearmint. We have CH3, and you can see that these molecules are just chirals of each other. They're just reflected across a plane, non-superimposable images of themselves. And you can see here that order is actually different. So in this case, it would be H2C, whereas on Caraway, this same molecule would be CH2. And the reason for that, the reason that they put the C closest to the bond is just to let you know that's the first. So that way we can easily work it out using the Cahn-Ingold prelog rules. So we take the same carbon molecule, carbon atom surrounded by 4 different groups. And once again, we can draw the missing hydrogen because it only has 4 single bonds. Based on its skeletal formula and its skeletal diagram, we can work out that there's a hydrogen behind it. So we do the same thing. We apply the same principle. We see that on this left branch, it goes carbon, obviously, from the carbon sensor. Carbon, 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 oxygen. So this is carbon, carbon, oxygen. This goes carbon, carbon, carbon. This one goes carbon, 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 carbon into hydrogen. So same thing, we denote this with a 4. Hydrogen's always going to be a 4 if it's by itself, so we have 4. Then we have 3 here, 2 here, and 1 here. Now if we just draw this straight off the branches, connecting it to the carbon atom, we have 4 here. Now 1, 2, 3 in the 3 directions. Now once again we go 1 to 2, 2 to 3, 3 back to 1. This is now clockwise direction. Therefore, spearmint is the same as our carbone. And we can apply this for all chiral molecules. So let's go on to our next example of lactate. So here we have lactate. Let's draw it out first. Trying to work out which one, the left or the right one, is R or S. So let's draw it out. Let's start with the right one, actually. And now what these sort of isosceles triangles actually mean is that normally for a skeletal formula, for this hydrogen or this not really for this hydroxide group, but you wouldn't normally need to draw it in. But the reason that you do using these isosceles triangles is to show that they are either on top or below of the molecular structure. This is actually important because it lets us know things like whether it's an R or S chiral. So we complete this. Now this diagram already tells us that this is a central carbon atom, but we do want to work out why that is. So here we have a few possibilities, possibles as to which carbon atom it could be. It's either this one or this one. In this case, it wouldn't really be fitting because you would have oxygen for both of them, so it has to be this. So here it's quite convenient because once again, the hydrogen group is behind us. So you could apply the same principle. We know it's behind us because of this dashed line. This dashed line indicates that it's behind us. If it's filled in, then we then know that it's above the molecule. So we then apply the same principle. We go carbon to carbon, carbon to oxygen in the hydroxide group, and carbon to carbon. Now this carbon to carbon also goes carbon to carbon on both left and right end trails. Instead here it goes carbon hydrogen, but here it goes carbon oxygen. So here we rank them again. We start off with oxygen because that's larger than either of these. So it goes 1. Here we go carbon oxygen, so that's 2. Here we go carbon hydrogen, so that's 3. And of course hydrogen by itself is always going to be 4, so we leave that there. So this is already behind us, so this is quite convenient. Now we apply the same rule, same principle once again. 1 to 2, 2 to 3, and 3 back to 1. This lets us know that this is R lactate. Now the next one I actually think is a bit tricky, but we'll try to work it out. Let's draw it out again. Now the reason I say this is a bit tricky is here we actually have one instance where the hydrogen molecule, or our lowest MR group, so we're always going to denote this with a 4, is not actually behind us. It's not behind us, so we'll go ahead and still order them from 1 to 3 first, the remaining ones. So this is central carbon. There's oxygen, hydrogen. From our previous example, we know that this is the heaviest. Then we have carbon oxygen, our second, and carbon hydrogen, which is our third. Now, what we want to do is place this number 4 on the back side. So what we can actually do, it's a lot easier to try to visualize it as an actual molecule in front of you, is we want to try to sort of transpose it, try to rotate it so that this lightest molecule, this hydrogen, will be behind us. So if it's on top of this molecule, we want to try to turn it. Imagine a ball, and you're trying to flip it in front of you. Flip it in front of you so that it turns so that it turns downward, sort of like that. So this instead will be on the bottom of the molecule, or behind us, in place of this HO. So this allows this H free C molecule to actually go on top in a way. We're sort of flipping it across the x-axis. So this would leave us with this sort of an arrangement from 1 to 2 to 3 like that, where this denotes this, and this denotes this, and this denotes this. This is now on top, and these two are on the left and right. And so using the same rules, we can then find out whether it's clockwise or counterclockwise. In this case, going this way would indicate anti-clockwise, so therefore this would be S-lactate. Sometimes, if you're under time conditions or this is difficult, an easy thing to do is try to visualize it with the two molecules, such as, so as in our first example, visualize it with the two molecules the other way around, and whatever that is, whether it's R, whether it's R or whether it's S, you just inverse that, and you'll get the answer. I think that's about it. As long as you remember to order them 1 to 4 on decreasing MR. Place the lowest MR behind, and find direction of 1 to 3 with 2 in the middle. That will always be either clockwise or anti-clockwise. You'll always get an answer with it being R or S.